There is a boundary in space that no human will ever cross. Not because we lack the technology, not because we lack the will, but because the universe itself is expanding, carrying distant galaxies away from us faster than light can travel, faster than any spacecraft could ever move. No matter how advanced our civilization becomes, no matter how many millennia pass, no matter what miraculous technologies we develop, there are places in the cosmos we will never reach, stars we will never visit, galaxies we will never explore. Tonight, we're going to contemplate the farthest distance humanity can ever travel. We'll journey from our small blue planet outward, step by step, boundary by boundary, until we reach the ultimate limit, the edge of our cosmic horizon. This is a story about distance, about time, about the strange geometry of an expanding universe, and ultimately, about what it means to be a small civilization in an incomprehensibly vast cosmos. It's also a story about limits. We don't often think about limits in our daily lives. We assume that with enough effort, enough ingenuity, enough time, we can achieve anything. And in human affairs, that's often true. But the universe has hard limits. Physical laws that cannot be broken, no matter how advanced our technology becomes. The speed of light is one such limit. The expansion of space is another. These limits define what's possible. They determine the ultimate reach of any civilization, no matter how advanced. And understanding them is both humbling and liberating. Humbling because we cannot overcome them. Liberating because what lies within them is still almost unimaginably vast. Let your breathing slow. Let your thoughts drift. And let's begin this journey together. We start, as all journeys must, at home. Earth orbits the Sun at a distance of about 150 million kilometers. This distance is so fundamental to astronomy that we've given it a special name, the astronomical unit, or AU. It's our cosmic yardstick, the baseline from which we measure everything else. One astronomical unit takes light about 8 minutes to cross. When you look at the Sun, you're seeing it as it was 8 minutes ago. The photons striking your eyes began their journey before you started reading this paragraph. This is the first lesson of cosmic distance. We never see anything as it is. We only see things as they were when the light left them. The farther we look, the deeper into the past we see. At 1 astronomical unit from Earth, we find our moon, actually much closer, only about 1¼ light seconds away. Astronauts have walked there. 12 humans have stood on lunar soil, looked up at the blue marble of Earth hanging in the black sky, and felt the profound isolation of being somewhere else. The moon is the farthest humans have ever travelled, about 384,000 kilometers, a distance that takes light just over 1 second to cross. In the grand scheme of the cosmos, we have barely left our front porch. Beyond the moon lies the rest of our solar system. Mars, the next obvious destination, orbits at about 1½ astronomical units from the Sun. At its closest approach to Earth, Mars is roughly 55 million kilometers away, about 140 times farther than the Moon. We've sent robots to Mars, dozens of them. Some have failed, others have succeeded spectacularly, rolling across rusty plains, climbing ancient mountains, and drilling into alien rock. But no human has ever made the journey. At the speed of our current spacecraft, reaching Mars takes about 7 months. That's 7 months of travel through the void, far from any help, exposed to cosmic radiation and the psychological toll of isolation. It's difficult, but it's achievable. Mars is within our reach, if we choose to reach for it. Let me linger on Mars for a moment, because it represents the first real test of our ability to expand beyond Earth. Mars is a cold, dry world with an atmosphere too thin to breathe and no magnetic field to shield against radiation. Its surface is rust-colored, stained by iron oxide, the same compound that makes blood red. Ancient river channels suggest it once had flowing water, perhaps even oceans. Today, that water is locked in polar ice caps and frozen beneath the surface. We've been exploring Mars with robots for decades. The first successful landing was Viking 1 in 1976. Since then, we've sent orbiters to map the planet from above and rovers to crawl across its surface, tasting the soil and photographing the landscape. The latest rovers, Curiosity and Perseverance, are car-sized laboratories on wheels. They've climbed mountains, drilled into rocks, and searched for signs of ancient microbial life. They've found organic molecules, seasonal methane variations, and evidence that Mars was once warm and wet. But no human has ever walked on Mars. No human has ever stood on that rust-colored soil, looked up at the butterscotch sky, and watched the tiny sun set over alien mountains. That will change, probably within the next few decades. NASA, SpaceX, and other agencies are developing the technology to send humans to Mars. The journey would take about 7 months each way, with a stay of perhaps 18 months waiting for the planets to realign for the return trip. It's dangerous. The first astronauts might die from equipment failure, from radiation exposure, from the 1,000 things that could go wrong in an environment utterly hostile to human life. But some will volunteer anyway, drawn by the same impulse that pushed explorers to cross oceans and climb mountains. When they arrive, they'll be the farthest humans have ever traveled from home. About 55 million kilometers at closest approach, over 100 times farther than the Moon. Communication delays will make them effectively independent. A message takes between 4 and 24 minutes to travel between Earth and Mars, depending on orbital positions. They'll have to solve their own problems, make their own decisions, live or die by their own competence. This is the first step, the first real step beyond our birth world, and it's almost within our grasp. Beyond Mars lies the asteroid belt, a ring of rocky debris left over from the solar system's formation. Millions of rocks orbit here, ranging from dust grains to dwarf planets. Ceres, the largest, is nearly 1,000 kilometers across, large enough to be spherical, but still tiny compared to the planets. The asteroid belt was once thought to be the remains of a shattered planet. We now know it's the opposite, material that never coalesced into a planet because Jupiter's gravity stirred it up, preventing the rocks from merging. Some asteroids are rich in metals: iron, nickel, platinum. A single metallic asteroid might contain more platinum than has ever been mined on Earth. Future civilizations might mine these rocks, extracting resources without the environmental cost of terrestrial mining. Beyond the asteroid belt, the character of the solar system changes. The inner solar system is warm and rocky. The outer solar system is cold and gaseous. The dividing line is marked by Jupiter, the largest planet, a world so massive it could swallow all the other planets combined and still have room to spare. Then the gas giants. Jupiter at 5 astronomical units, Saturn at nearly 10. These enormous worlds have their own systems of moons, dozens of them, some larger than planets, some harboring oceans beneath their icy shells. Jupiter is a failed star, a world that almost made it. If it had gathered about 80 times more mass during its formation, it would have ignited hydrogen fusion and become a red dwarf, turning our solar system into a binary star system. Instead, it fell short, becoming the largest planet rather than the smallest star. Jupiter's atmosphere is a chaotic swirl of storms, the most famous being the Great Red Spot, a hurricane that has raged for at least 400 years and is large enough to swallow Earth whole. Deeper down, the atmosphere transitions from gas to liquid to a strange metallic state, where hydrogen is so compressed it conducts electricity like a metal. Jupiter has at least 95 moons. The four largest, Io, Europa, Ganymede and Callisto, were discovered by Galileo in 1610 and revolutionized our understanding of the cosmos. They showed that not everything orbits Earth, providing evidence for the heliocentric model. Today, we know these moons are worlds in their own right. Io is the most volcanically active body in the solar system, its surface constantly reshaped by eruptions driven by tidal heating from Jupiter's gravity. Europa has a global ocean beneath its icy shell, kept liquid by the same tidal forces. That ocean might harbour life. Not complex creatures, perhaps, but microbes, surviving in the darkness far from the sun. Europa is one of the most promising places in the solar system to search for extraterrestrial life. NASA is planning a mission called Europa Clipper, which will study the moon in detail, looking for signs of habitability and perhaps even biosignatures. Jupiter is so far from the Sun that light takes about 43 minutes to make the journey. When the Juno spacecraft sends data back to Earth from Jupiter orbit, mission controllers must wait nearly an hour for signals to arrive. Commands sent to the spacecraft take equally long to reach it. This is the tyranny of distance. Even at the speed of light, the fastest speed possible in our universe, communication takes time. And as we venture farther, that time grows. Saturn lies at nearly 10 astronomical units, about 80 light minutes from the Sun. It's best known for its rings, vast bright disks of ice and rock that extend hundreds of thousands of kilometers, but are only tens of meters thick. Seen edge on, the rings virtually disappear. The rings are not permanent. They're slowly raining down onto Saturn, pulled in by gravity, and may disappear entirely within a few 100 million years. We're fortunate to live in an era when Saturn has rings. 1 billion years from now, it might just be another gas giant. The Cassini spacecraft spent 13 years exploring Saturn and its moons, revealing wonders beyond imagination. It discovered geysers on Enceladus, jets of water ice erupting from cracks near the moon's south pole, spraying material into space. These geysers suggest a subsurface ocean, kept liquid by tidal heating, potentially habitable. Cassini also explored Titan, Saturn's largest moon, a world with a thick atmosphere, the only moon in the solar system with a substantial one. Titan's atmosphere is mostly nitrogen, like Earth's, but much colder. Lakes and seas of liquid methane and ethane dot its surface, fed by methane rain. It's an alien world with a hydrological cycle, but one based on hydrocarbons rather than water. At the end of its mission, Cassini was deliberately crashed into Saturn's atmosphere to prevent any possibility of contaminating the potentially habitable moons. As it fell, it transmitted data until the very last moment, measuring the composition and structure of Saturn's upper atmosphere. But even Saturn is just a stepping stone. Beyond it lie Uranus and Neptune, the ice giants, at 20 and 30 astronomical units respectively. Neptune is so far from the Sun that light takes over 4 hours to make the journey. At Neptune's distance, the Sun is just a bright star, still the brightest object in the sky, but no longer the overwhelming presence it is on Earth. The warmth is gone, the light is thin. You are truly in the outer darkness. Beyond Neptune lies the Kuiper Belt, a vast ring of icy bodies extending from 30 to 50 astronomical units. Pluto orbits here, along with thousands of other frozen worlds. New Horizons flew past Pluto in 2015, revealing a surprisingly complex world with mountains of water ice, glaciers of nitrogen, and a thin atmosphere. New Horizons is still travelling outward, now more than 50 astronomical units from the Sun. It takes over 7 hours for its signals to reach Earth. And yet, in cosmic terms, it has barely begun its journey. The edge of the solar system is not precisely defined, but one useful boundary is the heliopause, the point where the solar wind, the stream of charged particles flowing outward from the Sun, finally gives way to the interstellar medium. Voyager 1 crossed this boundary in 2012, becoming the first human-made object to enter interstellar space. It was about 121 astronomical units from the Sun at the time, over 11 billion miles, a distance light takes about 17 hours to cross. Voyager 1 is now the most distant human artifact in existence. It carries a golden record containing sounds and images from Earth, a message in a bottle thrown into the cosmic ocean. The golden record was the brainchild of Carl Sagan and a small team who assembled it in just 6 weeks. It contains greetings in 55 languages, music from around the world, Bach, Beethoven, Chuck Berry, traditional songs from Peru and Japan and Senegal, and 116 images depicting life on Earth. The chances of any alien civilization finding the golden record are vanishingly small. Space is simply too vast, the probe too tiny. Voyager will drift through the galaxy for millions of years, passing through the empty spaces between stars, probably never encountering anything. But that wasn't really the point. The golden record was a message to ourselves as much as to any hypothetical extraterrestrials. It was a statement of who we are, what we value, what we hope to share with the cosmos. It was optimism, encoded in gold and copper, flung into the void. Voyager's nuclear batteries are slowly dying. By the mid-2030s, there won't be enough power to run any instruments. The spacecraft will fall silent, continuing its journey in darkness. But even silent, it will still be travelling, still carrying that golden record, still representing humanity in the interstellar void. In about 40,000 years, Voyager 1 will pass within about 1.6 light-years of a star called Gliese 445. It won't stop there. It's not aimed at any particular destination, just travelling outward. In about 300,000 years, it will pass within about 4 light-years of a star called TYC 3135-52-1. These are not close approaches by interstellar standards, but they represent Voyager's continuing journey, carrying its message through the galaxy long after everyone who built it has turned to dust. But even Voyager, travelling at 17 kilometers per second, will take tens of thousands of years to reach the nearest stars. And those stars are just next door, cosmically speaking. Let's talk about the stars. The nearest star system to our Sun is Alpha Centauri, a triple star system about 4.4 light-years away. Alpha Centauri is not a single star, but three, bound together by gravity. Alpha Centauri A and B are a binary pair, orbiting each other every 80 years. They're similar to our Sun. A is slightly larger and brighter, B slightly smaller and dimmer. The third member, Proxima Centauri, is a tiny red dwarf, orbiting the main pair at a vast distance, about 13,000 astronomical units, or about a fifth of a light-year. Proxima is actually the closest individual star to our Sun, slightly nearer than the AB pair. In 2016, astronomers discovered a planet orbiting Proxima Centauri. Called Proxima b, it's roughly Earth-sized and orbits in the habitable zone, the region where liquid water could exist on the surface. This was electrifying news. The nearest star has an Earth-sized planet in the habitable zone. If we ever develop interstellar travel, Proxima b might be our first destination. But habitable zone doesn't mean habitable. Proxima Centauri is a flare star, prone to violent outbursts that might strip away any atmosphere and bombard the surface with radiation. The planet is probably tidally locked, with one face always toward the star and one face always in darkness. Conditions might be harsh beyond anything on Earth. Still, it's a target, a destination, a reason to develop the technology for interstellar travel. A light year is the distance light travels in 1 year, about 9.5 trillion kilometers. 4.4 light years is roughly 40 trillion kilometers, a distance so vast that our usual units become meaningless. If the Sun were a grain of sand on a beach in Los Angeles, Alpha Centauri would be another grain of sand in San Francisco. The space between would be empty. No other grains, no other objects, just void. At Voyager 1's current speed, reaching Alpha Centauri would take about 70,000 years. 70,000 years ago, humans were painting on cave walls and hunting mammoths. Our entire recorded history, every empire, every civilization, every scientific discovery, fits within the last 5,000 years. No chemical rocket will ever bridge interstellar distances in human timescales. The energy requirements are simply too enormous, the speeds too slow. Let me explain why. Rockets work by throwing mass out the back. The faster you throw the mass, and the more of it you throw, the faster the rocket goes. This relationship is described by the Tsiolkovsky rocket equation, one of the most important equations in spaceflight. The problem is that fuel has mass. To carry more fuel, you need more fuel to accelerate that fuel. It's a vicious circle that leads to exponentially increasing fuel requirements for higher speeds. For chemical rockets, the kind we use today, the exhaust velocity is limited by the energy released in chemical reactions. No matter how clever your rocket design, you can't exceed this limit, and that limit is far, far too slow for interstellar travel. To reach Alpha Centauri in a reasonable time using chemical rockets, you'd need a fuel-to-payload ratio so extreme that the spacecraft would be almost entirely fuel. A rocket the size of the observable universe wouldn't be enough to accelerate a single atom to the required speed. Chemical rockets can take us to Mars. They can take us to the outer planets, but they cannot take us to the stars. We need something better. Nuclear propulsion offers one possibility. Instead of chemical reactions, you use nuclear fission or fusion to heat propellant and expel it at much higher velocities. NASA tested nuclear thermal rockets in the 1960s, and they worked, achieving exhaust velocities 2 to 3 times higher than the best chemical rockets. But even nuclear thermal rockets are too slow for interstellar travel. You'd still need fuel masses that are impractical. More promising is nuclear pulse propulsion, essentially detonating nuclear bombs behind your spacecraft and riding the shockwaves. This sounds insane, and it is, but the physics works. Project Orion, studied in the 1950s and 60s, concluded that a nuclear pulse ship could achieve about 3 to 5% of light speed, fast enough to reach Alpha Centauri in about a century. The problems are practical and political rather than physical. Detonating thousands of nuclear weapons would create radioactive fallout. Treaties prohibit nuclear explosions in space, and engineering a ship that can survive thousands of nuclear blasts is, to put it mildly, challenging. Fusion propulsion might work better. If we can achieve controlled fusion, the process that powers the sun, we could create rockets with exhaust velocities of thousands of kilometers per second. Fusion rockets might reach 5 to 10% of light speed. The catch is that we haven't achieved controlled fusion yet, despite decades of trying. And even if we do, engineering a fusion reactor small enough to put on a spacecraft is an enormous challenge. Antimatter propulsion is the ultimate in theoretical efficiency. When matter meets antimatter, they annihilate completely, converting all their mass to energy. No other reaction is so efficient. But antimatter doesn't exist naturally in significant quantities. We have to manufacture it particle by particle in accelerators. The total amount of antimatter ever produced by humanity is measured in nanograms. To fuel an interstellar spacecraft would require tons, which would take trillions of years to produce at current rates. Light sails offer a different approach. Instead of carrying fuel, you let light push you. A giant thin sail reflecting sunlight, or better, a powerful laser beam, could accelerate a spacecraft to significant fractions of light speed. This is the principle behind Breakthrough Starshot, a project aiming to send tiny probes to Alpha Centauri within a generation. The probes would be chip-sized, weighing just a few grams, attached to thin reflective sails. A powerful ground-based laser array would push them to about 20% of light speed. At that velocity, Alpha Centauri is about 20 years away. The probes would fly through the system, snap pictures, and transmit data back to Earth. We could have images of planets around another star within our lifetimes. But Starshot probes are tiny, too small to carry humans, too fast to stop. They're flybys, not visits. For actual human travel, we need something more. But let's imagine we develop better technology. Fusion drives, perhaps, or antimatter propulsion, or light sails pushed by powerful lasers. Let's imagine we can accelerate a spacecraft to 10% of the speed of light, 30,000 kilometers per second, 100 times faster than any probe we've ever built. At that speed, Alpha Centauri is 44 years away, a human lifetime. Astronauts who departed in their 20s might arrive in their 60s, aged and weary, but still alive to see an alien sun. This is technically possible, if extraordinarily difficult. Projects like Breakthrough Starshot are already exploring how to send tiny probes to Alpha Centauri within a generation. Sending humans would be harder by orders of magnitude, but not forbidden by physics. So Alpha Centauri is within our potential reach. Difficult, yes. Expensive, certainly, but not impossible. What about further? Our galaxy, the Milky Way, contains somewhere between 100 billion and 400 billion stars. They're arranged in a vast spiral disk about 100,000 light-years across, with a central bulge and sweeping arms of gas, dust, and stars. If you could see the Milky Way from outside, it would look like a giant pinwheel, a flat disk with spiral arms wound around a bright central bulge. Our Sun sits in one of the minor arms, called the Orion Arm, about 26,000 light-years from the galactic center. The galactic center is invisible to optical telescopes because there's too much dust between us and it. But radio waves and infrared light can penetrate the dust, revealing what lies at the heart of our galaxy, a supermassive black hole called Sagittarius A star, with a mass of about 4 million suns. This black hole is quiet now, barely noticeable except for the orbits of stars around it. But millions of years ago, it might have been active, swallowing gas and matter, blazing with the light of a quasar. It might become active again someday, when fresh material falls in. The stars of the Milky Way are not evenly distributed. They cluster in spiral arms, concentrating in regions where gas is dense enough to form new stars. Between the arms, stars are sparser, still present, but fewer and farther between. Our Sun orbits the galactic center once every 230 million years, a period sometimes called a galactic year. The Sun has completed about 20 galactic orbits since it formed. Dinosaurs lived about 1/4 of a galactic year ago. At 10% of light speed, crossing the entire galaxy would take about 1 million years. That's longer than our species has existed. Homo sapiens emerged roughly 300,000 years ago. 1 million years ago, our ancestors were still Homo erectus. Could a civilization survive for 1 million years? Could it maintain the continuity of purpose needed to complete such a journey? These are not just engineering questions, but questions about the nature of civilization itself. Human societies tend to rise and fall on timescales of centuries. Empires last hundreds of years, rarely thousands. The oldest continuous civilizations on Earth are measured in a few millennia at most. A journey lasting 1 million years would require not just technological capability, but social stability on timescales we've never achieved. It would require institutions that persist, knowledge that transmits reliably, and purpose that survives across tens of thousands of generations. Perhaps. Life on Earth has existed for nearly 4 billion years. Some species have persisted for hundreds of millions of years with little change. A technological civilization, if it could avoid self-destruction, might endure for geological timescales. But a 1 million-year journey is qualitatively different from a 40-year journey. It requires not a spacecraft, but a self-sustaining world, a generation ship, carrying a population that reproduces and dies and reproduces again, passing knowledge and purpose from parent to child across tens of thousands of generations. It requires a commitment unlike anything in human history. It requires accepting that the people who launch will never see the destination, and the people who arrive will have no living memory of departure. And yet, it's possible. The galaxy is within our reach if we're willing to reach for it across deep time. But what about beyond the galaxy? The Milky Way is just one galaxy among hundreds of billions in the observable universe. The nearest large galaxy, Andromeda, is about 2.5 million light-years away. At 10% of light speed, reaching Andromeda would take 25 million years. 25 million years ago, the first great apes were just appearing. Primates were small and primitive. The mammals that would eventually become humans were unrecognizable. An entire evolutionary lineage, from early primate to Homo sapiens, fits within the time it would take to reach Andromeda. And Andromeda is close as galaxies go. It's part of our local group, a small cluster of galaxies bound together by gravity. The local group contains about 80 galaxies, ranging from the two giants, the Milky Way and Andromeda, to dozens of tiny dwarf galaxies. The local group spans about 10 million light-years. At our hypothetical 10% light speed, crossing it would take 100 million years. That's longer than the age of the dinosaurs' reign on Earth. Beyond the local group lies the rest of the universe. Galaxy clusters, superclusters, filaments and voids stretching across billions of light-years. The observable universe is about 93 billion light-years in diameter, containing roughly 2 trillion galaxies. At 10% of light speed, crossing the observable universe would take nearly 1 trillion years. That's about 70 times longer than the current age of the universe itself. These numbers are so large they lose meaning. We can write them down, but we cannot truly comprehend them. The universe is simply too big for human intuition. But here's the strange thing, the thing that changes everything. Even these vast distances are not the true limit. The universe is expanding. And this changes what distance means in ways that seem almost like cheating. Let me explain. In 1929, astronomer Edwin Hubble made one of the most important discoveries in the history of science. He observed that distant galaxies are moving away from us, and that the farther away a galaxy is, the faster it's receding. Hubble didn't start out looking for cosmic expansion. He was trying to measure the distances to spiral nebulae, fuzzy patches of light that astronomers had been debating for decades. Were they nearby gas clouds within our own galaxy? Or were they separate island universes far beyond the Milky Way? To answer this, Hubble studied Cepheid variable stars, stars that pulsate in a regular rhythm, with their brightness varying predictably over days or weeks. The period of a Cepheid's pulsation is related to its intrinsic brightness. By measuring the period, you can determine the true brightness. By comparing the true brightness to the apparent brightness, you can calculate the distance. Hubble found Cepheids in the Andromeda Nebula and determined that it was about 1 million light-years away, far beyond the edges of the Milky Way. The spiral nebulae were indeed separate galaxies, and the universe was vastly larger than anyone had imagined. But Hubble also noticed something else. When he examined the light from distant galaxies, it was shifted toward the red end of the spectrum, redshifted. This indicated the galaxies were moving away from us, their light stretched by their motion. The amount of redshift was proportional to distance. Nearby galaxies had small redshifts. Distant galaxies had large redshifts. The farther away a galaxy, the faster it was receding. This wasn't because galaxies are flying through space away from a central point. It was because space itself is stretching, carrying galaxies apart like dots on an inflating balloon. Imagine drawing dots on a balloon, then blowing it up. Each dot sees every other dot moving away. There's no center to the expansion. Every point is equivalent. That's what's happening to the universe, in 3 dimensions rather than 2. The expansion of the universe is not like an explosion, with debris flying outward from a center. There is no center. Every point in space sees every other point moving away. The universe is expanding everywhere, uniformly, as if the fabric of space itself is being stretched. The rate of this expansion is described by the Hubble constant, about 70 kilometers per second per megaparsec. A megaparsec is about 3.26 million light-years. This means that for every 3.26 million light-years of distance, galaxies are receding at an additional 70 kilometers per second. At first, this seems modest. 70 kilometers per second is fast by everyday standards, but it's only about 0.02% of the speed of light. Surely we could overcome this. But here's the key. The recession velocity increases with distance. At 32 million light-years, galaxies recede at 700 kilometers per second. At 320 million light-years, 7,000 kilometers per second. At 3.2 billion light-years, 70,000 kilometers per second, about 23% of light speed. At about 14 billion light-years, the recession velocity reaches the speed of light. Beyond this distance, galaxies are receding from us faster than light itself. This seems to violate Einstein's rule that nothing can travel faster than light. But it doesn't, because the galaxies aren't traveling through space faster than light. Space itself is expanding, carrying them along. And there's no speed limit on the expansion of space. The distance at which recession velocity equals light speed is called the Hubble radius, and it's roughly 14 billion light-years. But here's where it gets even stranger. We can see galaxies beyond the Hubble radius. The light from these galaxies left billions of years ago, when they were closer and receding more slowly. That light has been traveling toward us ever since, even as space expanded around it. Some of that light eventually reached us, showing us galaxies that are now, at this moment, receding faster than light. The farthest objects we can see are about 46 billion light-years away. This is the radius of the observable universe, the sphere within which light has had time to reach us since the Big Bang. You might wonder, if the universe is only 13.8 billion years old, how can we see objects 46 billion light-years away? Shouldn't the light from anything beyond 13.8 billion light-years still be on its way? The answer lies in the expansion. When the light we see today left those distant objects, they were much closer to us. As the light traveled toward us, space expanded, stretching the light and increasing the distance. The light eventually arrived, but the objects that emitted it are now much farther away than they were when the light left. So, when we look at the cosmic microwave background, the oldest light in the universe, emitted about 380,000 years after the Big Bang, we're seeing the universe as it was when it was much smaller. But the matter that emitted that light is now about 46 billion light-years away, carried there by the expansion. This is confusing, and it's okay if your head hurts a little. Cosmic distances in an expanding universe don't work like everyday distances. The very concept of distance becomes slippery when space itself is changing. But these objects are not reachable. They're already receding faster than light. No signal we send will ever reach them. No spacecraft we launch will ever catch up. They're visible, but forever inaccessible. This creates a fundamental boundary, a cosmic horizon beyond which we can never travel, no matter how advanced we become. But it gets worse. The universe is not just expanding, the expansion is accelerating. In 1998, two independent teams of astronomers discovered that the expansion of the universe is speeding up over time. Distant supernovae were dimmer than expected, indicating they were farther away than they should be in a universe with constant expansion. This discovery was so unexpected that the teams double-checked their results for years before publishing. Surely they had made an error. Expansion should be slowing down, not speeding up, because gravity pulls matter together. But the data was clear. The expansion is accelerating and has been for about 5 billion years. The discovery earned the team leaders the Nobel Prize in Physics in 2011. It also created one of the biggest mysteries in modern physics. What is causing the acceleration? Something is pushing the universe apart, making it expand faster and faster. We call this something dark energy, though we have little idea what it actually is. The name is just a placeholder for our ignorance. Dark energy might be a property of space itself, Einstein's cosmological constant, a kind of energy inherent to empty space that pushes against gravity. Einstein originally proposed this constant in 1917 to create a static universe, then abandoned it when Hubble discovered expansion. Now it's back, though not for the reason Einstein intended. Or dark energy might be something more exotic, a dynamic field that varies across space and time, sometimes pushing harder and sometimes weaker. There are theoretical models for such fields, but no experimental evidence to distinguish between them. Whatever dark energy is, it makes up about 68% of the total energy content of the universe. Ordinary matter, stars, planets, you and me, makes up only about 5%. The rest is dark matter, another mysterious substance that we detect only through its gravitational effects. We live in a universe dominated by two forms of dark stuff we don't understand. The visible universe is a thin froth on an ocean of mystery. Whatever dark energy is, its effect is clear. The expansion of the universe is accelerating, and it will continue accelerating into the far future. This has profound implications for the maximum distance humanity can ever travel. Because the expansion is accelerating, the cosmic horizon is shrinking. Objects that are currently just within our potential reach will eventually cross the horizon and become permanently inaccessible. Right now, we can theoretically reach any object within about 16 billion light-years, if we could travel at nearly the speed of light and had an infinite amount of time. This is called the cosmic event horizon, the boundary beyond which signals we send today will never arrive. But because of accelerating expansion, this horizon is getting closer. Objects are constantly crossing it, falling away from us forever. Eventually, in the deep future, almost everything in the universe will be beyond our reach. Let me paint you a picture of what this means. Imagine a civilization vastly more advanced than ours that decides to explore the universe. They develop spacecraft that can travel at 99.9% of light speed. They have unlimited energy, unlimited time, and unlimited determination. They set out from their home galaxy, the Milky Way, aiming for the farthest reaches of the cosmos. In the first few million years, they spread through the local group. They colonize Andromeda, the Triangulum galaxy, and dozens of dwarf galaxies. The local group becomes their empire, their home. They keep going. They reach the Virgo cluster, about 50 million light-years away, then the Coma cluster, about 300 million light-years. Each journey takes longer than the last, not just because the distances are greater, but because expansion is carrying their targets away. As they travel, they notice something troubling. The distant galaxies they aimed for are getting farther away, even as they approach. Space is stretching faster than they can cross it. At some point, they reach a boundary. No matter how fast they travel, the galaxies ahead are receding faster. They're running on a cosmic treadmill, making progress but unable to keep up with the expansion. They can never cross this boundary. No technology can help them. No determination can overcome it. The universe itself has drawn a line and said, this far and no farther. Our hypothetical civilization has reached the maximum distance they will ever travel. Where is that boundary? The calculations are complex, depending on the exact values of cosmological parameters and assumptions about future expansion. But roughly speaking, the farthest structures humanity could ever reach, traveling at nearly the speed of light, starting now, lie about 16 to 18 billion light-years away. This is our cosmic horizon. Everything within it is, in principle, accessible. Everything beyond it is forever out of reach. 16 billion light-years sounds enormous, and it is. It encompasses millions of galaxy clusters, billions of galaxies, countless trillions of stars, more worlds than we could ever explore, even with unlimited time. But it's only a fraction of the observable universe, which extends to 46 billion light-years. And it's an infinitesimally tiny fraction of the entire universe, which may be infinite, or at least vastly larger than what we can see. The accessible universe is like an island in an infinite ocean. We can explore every grain of sand on the island, but the ocean, stretching to the horizon and beyond, will always remain beyond our reach. Let's contemplate what lies within our island. The local group, our immediate neighborhood, contains about 80 galaxies. The Milky Way and Andromeda are the giants, but there are dozens of smaller companions. The large and small Magellanic Clouds, visible from Earth's southern hemisphere as fuzzy patches of light. The Triangulum Galaxy, the third largest in the group, and many dwarf galaxies too faint to see without telescopes. Over the next few billion years, the local group will change dramatically. Andromeda is actually approaching us, one of the few galaxies that's blue-shifted rather than red-shifted. In about 4 to 5 billion years, the Milky Way and Andromeda will collide and merge, forming a new, larger galaxy, sometimes called Milkomeda or Milkdromeda. The collision will be spectacular if anyone is around to see it. But it won't be catastrophic for individual stars. Galaxies look solid when we photograph them, but they're mostly empty space. The average distance between stars in the Milky Way is about 4 light-years. When two galaxies merge, their stars pass through each other like two swarms of bees, rarely colliding directly. What does happen is gravitational chaos. The combined gravity of billions of stars, all pulling on each other, reshapes both galaxies. Stars are flung outward into intergalactic space. Others are hurled inward toward the merged galactic center. The neat spiral structures unwind and smear out, eventually settling into a giant elliptical blob. Computer simulations show what the merger might look like. First, the two spirals approach, distorting as they come. Then they pass through each other, trailing long streamers of stars and gas. They swing around, fall back together, pass through again. Over hundreds of millions of years, the oscillations damp out, and the merged galaxy settles into its final shape. From Earth, or wherever our descendants live, the view would be extraordinary. Andromeda, now a faint smudge barely visible to the naked eye, would grow larger decade by decade, century by century. Eventually, it would fill a significant portion of the sky. a vast spiral of billions of stars, slowly approaching. The actual merger would take hundreds of millions of years to complete. No human lifetime would see dramatic changes, but over geological time, the night sky would transform utterly. This merger won't be catastrophic for individual stars. Galaxies are mostly empty space. The stars are so far apart that direct collisions will be rare. But the gravitational interaction will reshape both galaxies, flinging some stars into intergalactic space and funneling others toward the new galactic center. Our Sun probably won't survive to see the merger. In about 5 billion years, it will exhaust its hydrogen fuel and expand into a red giant, likely engulfing Earth. Long before the galaxies merge, our home will be gone. But if humanity survives, if we spread to other stars, other worlds, our descendants might witness the merger from afar. They'll see the skies filled with the approaching spiral of Andromeda, growing larger over millions of years, until the two galaxies interpenetrate and become one. Eventually, all the galaxies of the local group will merge. Gravitational interactions will draw them together over tens of billions of years, forming a single giant elliptical galaxy. And then, something strange will happen. The rest of the universe will fade away. As expansion accelerates, distant galaxies will recede faster and faster. Their light will stretch to longer and longer wavelengths, shifting from visible to infrared to microwave to radio. Eventually, they'll cross the cosmic horizon and disappear entirely. From within our merged local group galaxy, the universe will appear empty. The cosmic microwave background will fade to imperceptibility. The night sky will contain only the stars of our own galaxy, and beyond them, nothing. Perfect, absolute blackness. A civilization arising at that time, trillions of years in the future, would have no way of knowing that other galaxies ever existed. They would look out at the void and conclude that their galaxy was the entire universe, an island of stars in an infinite sea of darkness. The evidence of the Big Bang, the expansion, the cosmic web of galaxies, all of it will be undetectable. The universe will have erased its own history. This is the deep future that awaits. Not a dramatic end, but a slow fade. A universe that empties out, leaving only isolated islands of matter, separated by unbridgeable gulfs of expanding space. But we're getting ahead of ourselves. Let's return to the present and ask, what does all this mean for humanity? We stand at a particular moment in cosmic history. The universe is young, only about 13.8 billion years old, compared to the trillions of years that may lie ahead. The galaxies are still visible, still relatively close, still theoretically accessible. If we're going to explore the cosmos, now is the time. Not now in the sense of this year or this century, but now in the sense of this cosmic epoch. The window is open. In the deep future, it will close. What might we achieve if we truly committed to cosmic exploration? Let's imagine a future, thousands or millions of years from now, where humanity has spread through the local group. We've colonized Mars and the moons of Jupiter and Saturn. We've built habitats in the asteroid belt and the Kuiper belt. We've sent generation ships to Alpha Centauri and beyond, establishing outposts around other stars. Over millions of years, These outposts have grown into civilizations of their own. They've adapted to their new environments, diverging from Earth-born humanity in culture, language, and perhaps even biology. But they remember their origin. They know they came from a small blue planet orbiting an ordinary yellow star. And they keep expanding. A wave of colonization spreads through the Milky Way at some fraction of light speed. A few percent, perhaps, limited by the physics of propulsion and the economics of settlement. But even at 1% of light speed, the entire galaxy can be colonized in about 10 million years. 10 million years sounds long, but it's brief on cosmic timescales. It's less than 0.1% of the universe's current age. In the blink of a cosmic eye, humanity, or whatever humanity becomes, could fill the Milky Way. And then they would reach for Andromeda. The journey to Andromeda would take about 2.5 million years at near light speed. But generation ships, or digital mines, or some technology we can't yet imagine might make it possible. The colonization wave would leap the intergalactic void and begin spreading through our neighbor galaxy. From there, the rest of the local group, the Triangulum Galaxy, the Magellanic Clouds, dozens of dwarf galaxies, each with its millions or billions of stars. Within a few 100 million years, the entire local group could be settled, every star visited, every habitable world colonized, every resource tapped. And then we would reach the boundary. Beyond the local group, the other galaxy clusters are receding. Some are still accessible if we left immediately and traveled at nearly light speed. The Virgo cluster, the Fornax cluster, the Coma cluster. They're still within our cosmic horizon. But the window is closing. Every moment we wait, the accessible universe shrinks slightly. Galaxies that are reachable today will not be reachable tomorrow. Not tomorrow in the literal sense, but in the cosmic sense, over millions and billions of years. If humanity is to maximize its reach, it must begin the journey as soon as possible. Every delay means galaxies lost, stars unreachable, worlds that will never know human presence. This is a strange kind of urgency. Not the urgent crisis of a disaster, but the slow urgency of opportunity slipping away. The universe is giving us a window, and the window is slowly closing. Whether we choose to leap through it is up to us. Of course, this assumes we survive. It assumes we avoid extinction from war, disease, asteroid impact, or some unforeseen catastrophe. It assumes we develop the technologies needed for interstellar and intergalactic travel. It assumes we maintain the will to explore across timescales that dwarf our recorded history. Let me linger on this point, because it's often overlooked in discussions of cosmic expansion. Survival is not guaranteed. Our species has existed for 300,000 years, but modern technological civilization is only a few centuries old. We've invented weapons capable of destroying ourselves. We're changing our planet's climate in ways we don't fully understand. New technologies, artificial intelligence, biotechnology, nanotechnology, create new existential risks even as they offer new possibilities. The 20th century saw 2 world wars, the invention of nuclear weapons, and multiple near misses that could have ended civilization. The Cuban Missile Crisis in 1962 brought us within hours of nuclear war. We survived more by luck than by wisdom. The 21st century will bring its own challenges: climate change, pandemic disease, resource depletion, geopolitical instability. Any of these could derail our cosmic ambitions or end them entirely. And even if we avoid human-caused catastrophe, the universe is not a safe place. Asteroid impacts have caused mass extinctions before and could do so again. Supernovae, gamma-ray bursts, and other cosmic events could sterilize our planet with little warning. The Earth, comfortable as it seems, is a fragile lifeboat in a hostile cosmos. Spreading beyond Earth is, in a sense, an insurance policy. A civilization confined to one planet is vulnerable to extinction from a single disaster. A civilization spread across many worlds is far more resilient. You'd have to destroy every outpost, every colony, every ark to wipe out the species entirely. This is the argument for space colonization, not as adventure or ambition, but as survival. As long as all our eggs are in one basket, we remain one catastrophe away from oblivion. Mars is the first step. Not because Mars is hospitable, it isn't, but because it's accessible. A self-sustaining colony on Mars would mean that even if Earth was destroyed, humanity would survive. The asteroid belt is the next step. The moons of Jupiter and Saturn, other star systems. With each expansion, we become more secure. Eventually, if we spread far enough, we become effectively immortal as a species. Individual civilizations might rise and fall, but the overall pattern would persist, adapting, evolving, enduring. This is the deeper reason to reach for the stars. Not glory, not curiosity, survival. These are enormous assumptions. Our species has existed for 300,000 years. Our technological civilization has existed for perhaps 300. We have no track record of planning across millions of years. And yet, the opportunity exists. The physics allows it. The universe, indifferent to our ambitions, has created a window through which we might, if we choose, spread across billions of light years. Whether we walk through that window, that is a choice for our descendants to make. Let me now describe what happens if we don't. If humanity remains confined to Earth, or even to the solar system, our long-term fate is sealed by astronomy. In about 1 billion years, the sun will have brightened enough to make Earth uninhabitable. The oceans will boil. The atmosphere will escape to space. Our planet will become a scorched, lifeless rock. In about 5 billion years, the sun will exhaust its hydrogen and expand into a red giant. It would engulf Mercury and Venus, and possibly Earth as well. Even if Earth survives, it will be a cinder, baked by a bloated, dying star. Eventually, the sun will shed its outer layers and collapse into a white dwarf, a dense, Earth-sized remnant that slowly cools over trillions of years. If we're still confined to this one solar system, our civilization ends when the sun does. But even if we spread through the galaxy, the long-term future is constrained by the fate of the stars themselves. Stars are not eternal. They're fueled by nuclear fusion, converting hydrogen to helium in their cores. When the fuel runs out, they die. Some quietly, fading to white dwarfs, others explosively as supernovae. The largest, most massive stars burn through their fuel quickly, lasting only millions of years. Smaller stars are more frugal, lasting billions of years. The smallest red dwarfs are so efficient that they can burn for trillions of years, far longer than the current age of the universe. But even red dwarfs will eventually exhaust their fuel, and new stars will eventually stop forming. Star formation requires gas, mostly hydrogen, to collapse under gravity and ignite fusion. The Milky Way still has substantial gas reserves and will continue forming stars for billions of years. But the rate of star formation has been declining since its peak about 10 billion years ago. Eventually, the gas will be used up or dispersed, and no new stars will form. Astronomers estimate that the last stars in the universe will form in about 100 trillion years. After that, the existing stars will gradually burn out, one by one, until the last red dwarf fades to darkness. This is the stelliferous era, the age of stars. It began shortly after the Big Bang and will last about 100 trillion years. We live near the beginning of this era, when stars are plentiful and the universe is bright. Let me help you feel the scale of this time. The universe is currently about 13.8 billion years old. The stelliferous era will last about 100 trillion years. So the universe is currently about 0.01% of the way through its starlit phase. If the stelliferous era were a single day, we would be in the first second after midnight. The stars have just begun to shine. The cosmic dawn was moments ago. We are living in the morning of the universe. Everything that will ever happen under starlight is still ahead of us. This should give you hope, if you're inclined toward hope. The universe is young. There is time, vast, unimaginable quantities of time, for civilizations to rise, spread, explore, and endure. Even if we fail, others might succeed. Even if Earth goes dark, other worlds might shine. The window is open. The stars are burning. The galaxies are accessible. And we are just beginning. After the stelliferous era comes the degenerate era, when the universe is populated by the remnants of dead stars, white dwarfs, neutron stars, and black holes. White dwarfs are the corpses of sun-like stars. When a star exhausts its fuel, it sheds its outer layers and the core collapses into a dense ball of carbon and oxygen, about the size of Earth but with the mass of the Sun. White dwarfs glow faintly from residual heat, but they have no energy source. Over trillions of years, they slowly cool, eventually fading to cold, dark balls of degenerate matter. Neutron stars are the corpses of more massive stars. When a star heavy enough to explode as a supernova dies, its core collapses beyond a white dwarf, crushing protons and electrons together to form neutrons. A neutron star is only about 20 kilometers across, but contains more mass than the Sun. It spins rapidly, emitting beams of radiation that we detect as pulsars. Neutron stars also slowly cool and fade over trillions of years. Eventually, they too go dark. Black holes are different. They don't radiate light, at least not from their interior. But in 1974, Stephen Hawking predicted that black holes slowly evaporate through a quantum mechanical process now called Hawking radiation. The details are complex, but the basic idea is that quantum fluctuations near the event horizon can create particle-antiparticle pairs. Sometimes, one particle falls into the black hole while the other escapes. The escaping particles carry away energy, causing the black hole to slowly shrink. For stellar mass black holes, this process is incredibly slow, much slower than the current age of the universe. But over unimaginably long timescales, every black hole will eventually evaporate. These objects still contain energy, and a sufficiently advanced civilization might harvest it. But the available energy is finite and will eventually be exhausted. After the degenerate era comes the black hole era, when black holes are the dominant objects in the universe. They slowly evaporate through Hawking radiation, converting their mass to energy over unimaginably long timescales. The largest black holes will take about 10 to the 100th power years to evaporate, a number so large it's meaningless to human intuition. And after the black hole era? The dark era. A universe of scattered particles, too dispersed to interact, too cold to form structures, expanding forever into infinite emptiness. This is the ultimate fate of the cosmos. Not a dramatic apocalypse, but a slow fade to darkness, stretched across timescales that make the current age of the universe seem like the first moment after the Big Bang. Against this backdrop, what is the meaning of our cosmic ambitions? Even if we colonize the entire accessible universe, every galaxy within our horizon, we are still confined to a finite island. And even that island will eventually go dark. Some might find this depressing. The universe doesn't care about us. Our greatest achievements will eventually be forgotten, erased by the heat death of the cosmos. Nothing we do will last forever. But there's another way to see it. The universe has given us a window. A brief, bright window in cosmic time, when stars shine and complexity flourishes, and minds can contemplate their own existence. This window will not last forever, but it will last for a very, very long time. Trillions of years, if we measure it by the lifetime of the smallest stars. And within that window, almost anything is possible. We can explore, we can learn, we can spread through the cosmos, experiencing wonders we can barely imagine. We can create meaning, even in a universe that has no intrinsic purpose. The fact that it will end doesn't diminish it. A symphony is not meaningless because it has a final note. A life is not worthless because it eventually ends. The meaning is in the experience, not the permanence. Perhaps that's the deepest lesson of cosmic distance. We are small, and the universe is vast. We are brief, and the cosmos is ancient. But within our small corner, within our brief moment, we can reach for the stars. And reach we should, because the window is open now. Because the galaxies are still visible, still accessible, still waiting. Because we are the first generation, perhaps one of only a few generations in cosmic history, with the knowledge and the technology to contemplate such journeys. Our descendants may look back on this era the way we look back on the age of exploration, a time when the universe was mapped, when the boundaries were discovered, when the first tentative steps were taken toward a cosmic future. Or they may look back with regret, wondering why we didn't reach farther when we had the chance. The choice is ours. The universe will not make it for us. Let me bring this back to the concrete. What are the actual distances we might reach? The answer depends on technology, time, and determination. Let me walk through it step by step, from the near future to the ultimate cosmic horizon. Within the next century, with technologies currently under development, we might realistically expand through our solar system. Mars colonies, asteroid mining, outposts on the moons of Jupiter and Saturn. Mars is about 7 light minutes away at closest approach. With current chemical rockets, the journey takes about 7 months. Humans might walk on Mars within the next decade or two. The asteroid belt lies between Mars and Jupiter, about 2 to 4 astronomical units from the Sun. Some asteroids are easier to reach than the Moon in terms of energy. They're in orbits that bring them close to Earth, allowing spacecraft to rendezvous with minimal fuel. Asteroid mining could provide the resources for further expansion. Water, metals, and organic compounds are all present in asteroids. A space-based economy might emerge, with habitats and factories orbiting in the belt. Jupiter and its moons lie about 5 astronomical units from the Sun, about 43 light minutes. The journey takes years with chemical rockets, but nuclear propulsion could reduce this to months. The moons of Jupiter, Europa, Ganymede, Callisto, might become outposts, even colonies. Saturn is about 10 astronomical units, nearly 90 light minutes. More distant, but still accessible. Titan, with its thick atmosphere and hydrocarbon lakes, might be the strangest human settlement in the solar system. The ice giants Uranus and Neptune lie at 20 and 30 astronomical units respectively. They're more challenging, colder, darker, farther. But even they are within reach for robotic missions and eventually for human presence. The Kuiper belt extends from about 30 to 50 astronomical units, populated by icy bodies like Pluto. Beyond that lies the Oort cloud, a vast sphere of comets extending perhaps halfway to the nearest stars. These regions are dark and cold, but they contain resources, water, ammonia, methane, that might support far future travelers. These are distances of billions of kilometers, vast by human standards, but tiny on the cosmic scale. We could travel them with chemical rockets, nuclear propulsion, or solar sails. The technology is challenging, but not impossible. Within the next 1,000 years, if we maintain our technological civilization, we might develop the capability for interstellar travel. Fusion drives, antimatter propulsion, or laser-pushed light sails could accelerate spacecraft to significant fractions of light speed. The nearest stars are a few light years away. At 10% of light speed, they're reachable within a human lifetime. The first probes might be followed by generation ships, carrying colonists to establish outposts around other suns. Within the next million years, we could spread through a significant portion of the galaxy. Colonization waves moving at a few percent of light speed would reach the galactic center in a few 100,000 years, and the far edge in a few million. 1,000,000 years is long for a human, but short for a species. Modern humans have existed for 300,000 years. In another 1,000,000 years, if we survive, we could fill the Milky Way. Within the next billion years, we could colonize the entire local group. Andromeda, the Magellanic Clouds, and dozens of dwarf galaxies could all harbor human or post-human civilizations. And what would we find there? This is one of the great unanswered questions. Are we alone? In a galaxy with hundreds of billions of stars, many with planets, some with conditions suitable for life, is Earth the only place where life emerged? The silence is puzzling. If other civilizations exist and have been expanding for millions or billions of years, why haven't we detected them? This is the Fermi paradox, named after physicist Enrico Fermi. There are many possible answers. Perhaps life is rare and we're nearly alone. Perhaps civilizations tend to destroy themselves before they can expand. Perhaps they're out there, but we can't detect them. Perhaps they've chosen not to expand. We don't know. But if we spread through the local group, we'll explore every star, visit every planet, search every moon for signs of life. We'll know whether we were alone all along or whether we share the cosmos with others. Either answer is profound. If we're alone, the local group is our inheritance, an empty stage waiting for us to fill it with life and mind. If we're not alone, we'll meet intelligences different from our own, exchange knowledge, perhaps form alliances or rivalries that span the galaxies. This is the realistic limit for our cosmic ambitions. At least, without exotic physics we don't yet understand. The local group is gravitationally bound, meaning it will eventually merge rather than fly apart. Everything within it is accessible, given enough time. Beyond the local group, the universe is expanding. The Virgo cluster, about 50 million light-years away, is still theoretically reachable if we left soon. But soon, in cosmic terms, means within the next few billion years. After that, the window closes. The farthest structures we could ever reach, even with perfect technology and unlimited time, lie about 16 to 18 billion light-years away. This is our cosmic horizon, the edge of the accessible universe. Everything within that horizon is potentially ours. Everything beyond it is forever unattainable. It's a strange kind of boundary. Not a wall we could touch, not a barrier we could see. Just a mathematical limit, defined by the expansion of space and the speed of light. A boundary that exists only because the universe is expanding faster than we could ever travel. And yet, what lies within that boundary is enough. More than enough. Billions of galaxies, trillions of stars. Countless worlds, countless mysteries, countless opportunities for discovery and growth. If humanity reaches even a fraction of that potential, we will have achieved something magnificent. We will have transformed ourselves from a single planet species, vulnerable to extinction, into a cosmic civilization spanning billions of light years. And if we don't? If we fail? If we destroy ourselves? If we never leave this one small world? Then the universe will continue without us. Other species, on other worlds, may make the journey we declined. Or perhaps no one will. Perhaps the cosmos will remain forever silent, a vast expanse of stars and galaxies with no one to appreciate them. That would be the greatest tragedy. Not the end of humanity, but the silencing of all consciousness. A universe that exists, but is never known. We have a responsibility, perhaps, to ensure that doesn't happen. To spread life and mind through the cosmos, not for our own glory, but so that the universe has witnesses, so that the stars are not just burning, but seen. This is a grand and perhaps arrogant thought, but it's also humbling. We are small, fragile, impermanent. And yet, we might be the universe's way of knowing itself. That's worth protecting. That's worth reaching for. Let your thoughts drift now. Let the numbers and distances fade into abstraction. You are on a small planet, orbiting an ordinary star in the suburbs of an ordinary galaxy. Above you, if the sky is clear, you can see a few thousand stars, a tiny fraction of the hundreds of billions in the Milky Way. Beyond those visible stars, invisible to the naked eye, lie the other galaxies. Andromeda is up there, a faint smudge if you know where to look. The Virgo cluster, the Coma cluster, the vast web of filaments and voids that make up the cosmic structure. All of it is out there. All of it is real. All of it is receding. and all of it is, in principle, within our reach. Not today, not tomorrow, but someday. If we choose. If we survive. If we reach. The universe has given us a gift, a window in time, a bright era when the stars shine and the galaxies are accessible. The window will not stay open forever, but it's open now. What will we do with it? That's a question for another night, another contemplation. For now, let it rest. Let your mind rest. The stars will be there tomorrow. The galaxies will be there tomorrow. The cosmic horizon will be there, slowly shrinking, but still vast, still full of possibility. And you will be there too, one small observer in an incomprehensibly vast cosmos, contemplating distances that dwarf human understanding. That's enough. That's more than enough. Sleep well. Dream of the stars. And know that the universe, for all its indifferent vastness, has produced at least one creature capable of wondering how far it can go. That creature is you. On a small planet, orbiting an ordinary star, in the suburbs of an ordinary galaxy, yet capable of contemplating the cosmos itself. There's something profound in that. Something that transcends the cold equations of distance and expansion. The universe didn't have to produce consciousness. It didn't have to create beings who could look out at the stars and wonder what lies beyond. But it did. And here we are, small, fragile, brief, yet aware. That awareness is precious. Perhaps the most precious thing in the cosmos. The ability to experience, to understand, to marvel at existence itself. Whether we spread to the stars or remain on this one small world, whether we endure for millions of years or vanish tomorrow, we have this moment, this chance to contemplate our place in an incomprehensibly vast universe. That's not nothing. That's everything. The distances are vast. The timescales are humbling. The limitations are real. But within those limitations, within the accessible universe bounded by the cosmic horizon, there is more wonder than we could experience in 1,000,000,000,000 lifetimes. That's the gift. That's enough. Let the numbers and distances fade now. Let the stars blur into a gentle glow behind your closed eyelids. Let the weight of cosmic contemplation settle into peaceful acceptance. We are small. The universe is vast, and somehow, impossibly, we exist. We think. We wonder. We dream. That's the greatest journey of all, the journey from mere existence to awareness. And you've already made it. Now rest. The stars will be there tomorrow. The galaxies will be there tomorrow. The cosmic horizon will be there, patient and eternal. And you will be there too, ready to wonder again. Good night.